recording. And then let me go back to the screen is showing. Okay, yes, okay. So welcome to Math 150 Multivariable Calculus. This class, I think, is terribly misnamed. This is your third calculus class. Please give me another department at this institution where your third class in the sequence is still listed as a 100 level course. You should really view this as at least a 200 level course. This is the third class in the sequence. If you want to become a math major or a STEM major, that is great. I'm happy to talk to you about opportunities, about things you can do next. If you want projects during the year to try things out, that's absolutely doable. If you want to just use this to supplement something in a related field, or if you're just intellectually curious, that's wonderful. There's a reason you're at a school like Williams to just look around and see what's out there. And so what I want to do today is talk a little bit about the mechanics of the course, which is the most enjoyable thing, of course, in the semester. And then talk a little bit about what will we actually be doing in this. I remember the first time I was teaching and one of my students was no longer born in my decade, the 70s. I finally was teaching someone born in the 80s. Then it was somebody born in the 90s. And it's just gotten progressively worse for me in terms of my connections to your pop culture and everything. Fortunately, I have a 10th grader and an 8th grader, so I have at least some intersections now. There have not been that many advances in the definition of the derivative in the last 100 years. That's pretty stable. What's the greatest change in calculus in the last, say, 50 years or 20 years? What might be very different for you than from when I was growing up? Online calculators. Thank you for not saying electricity or something like that, which my kids sometimes do. But it is extremely different how you are going to learn things than how I learned things. I learned how to use tables of integrals. I learned how to use tables of trig functions and log functions to look things up. There's value to that. A lot of modern technology is built on the lookup table. But a lot of the integration techniques that you have learned, how many of you took the BC Calc exam or the AB exam? So my son took it last year, and part of it was, can you do calculus? And then a good part of it was, now we assume you can do calculus if you have a calculator and now solve some problems. That's really where you want to be. You are not going to have going forward in life all of these integration techniques and integrals memorized. It's the 21st century. You're going to look it up. What you need to be able to do is know what's out there. You need to be able to figure out, what can I use to attack this problem? Is this similar to something I've seen before? Can I come up with a model, and will this model be solvable? As we get to opening day in baseball, I will give a lecture of applications of multivariable calculus to baseball. And it's actually where I've made a lot of my fame in the sabermetrics community. I want you to get to the point where you can use calculus to do things. So how many of you remember your integration techniques? Okay. So integration is probably the greatest lie. Calc 2 is probably the greatest deception of all math classes. When you leave, you think you can integrate. You can't. I can't either. We have to work very, very hard to give you functions that can be integrated in closed form. Most functions can't be integrated in closed form. And some of the functions you think you can integrate in closed form, you can only do so because we've given them nice names. So somebody give me a nice function to integrate. Sine. No. Sine is way down on the list. Nice function. You can be a smartass. Nicest function you can think of. Even easier than x. Even easier than 1. 0. Right? We can integrate the function 0 without any trouble. Then after that, we would have general constants. Then we would have x. Then we would have polynomials. And then after polynomials, now let's get to your sine. So what's the integral of sine? I'm sorry?
I kind of forgot the negative cosine.
So it's up to it's either cosine or negative cosine. The way I remember it is the derivative of cosine is minus sine. The derivative of sine is cosine if you use radians, not if you use degrees, if you use radians. You have to remember, where does the minus sign go? Derivative of cosine is not negative sign. Derivative of cosine is minus sign. That's where the minus sign goes. Derivative of cosine is minus sign. You can also think about the unit circle. If you start at the unit circle, if you start at 0 degrees, as you go up, cosine is decreasing, sine is increasing. If cosine is decreasing, we'll talk about this, then that means its derivative must be negative. How do you calculate the sine or the cosine of an angle? So this is how a mathematician does it, and how does somebody in the 21st century calculate the sine or cosine of an angle? Look online, take out your calculator, take out your phone, right? Some of you maybe even your watch, if you still have watches. But the way we actually find what sine or cosine is we have an infinite series expansion. There's only a few angles where we really know what sine or cosine is. Does anybody know what the good angles are? These come from good triangles. Anybody have any remembrance? Yes.
6, 2, 4.
Excellent. And can you speak in degrees rather than radians? I always do my calculation in radians. 45, 30, 60. Yeah, exactly. We can do those. Then we have the angle addition formulas and stuff like that. So we can go from 30 to 15. We can go from 45 to 22.5. We can play games like that. But if I give you an arbitrary angle, we actually have to use an infinite series for sine or cosine to evaluate it. And so when we say we know what sine and cosine are, yes, but only because we're defining an infinite series to be them. So while they're nice functions, or we consider them nice functions, they're really infinite series. That's going to be a big theme of this class. You're not supposed to have seen what's called Taylor series. And this is one of the big ideas of calculus, is you take something complicated and you approximate it with something simpler, and you just control how good the approximation is. So what's the simplest function you can think of? Straight line. And that's essentially what Calc 1 is we approximate functions with straight lines. What might do a better job than a straight line? What's your next simplest shape after a line? Quadratic. And then we say, well, what's the best quadratic that approximates? And you can keep going and going and going. And so that's going to be a big theme of this class, is when can we replace something complicated with a series of simpler items and then piece it together and keep track of the error. Is anybody aware of roughly how much money Elon Musk paid for Twitter? Approximately. How much? Or the US national deficit. Those are two big numbers.
31.4 trillion.
Good. Oh, you gave me the 0.4. Excellent. Okay, so 31.4 trillion. Turns out that there was a mistake. There were a bunch of checks the US government forgot to cash. We actually have an extra $10 million than we thought. Does this change anything for the US government? The US government now has $10 million more than we thought. Yeah, not at all. Does it change for anybody in this room if all of a sudden I tell you you have an extra $10 million that you weren't aware of? If it doesn't, please see me after class. Or if you want, we can go outside right now. Right? When you talk about numbers, it's always relative. You know, $10 million out of 31 trillion, it's not even noticeable. $10 million out of what we have, very noticeable. And so when we're trying to approximate complicated functions with simple functions, we want to get a sense of how bad is the error? What can we do with these approximations? These are going to be very difficult calculations. It's hard to integrate something in closed form. Can we come up with good approximations that will do enough of a job for what we need? One of the videos I'm going to share a little bit later is a whoopsie from Apollo 12. Is they didn't want to have any of the space junk getting in the way of future missions. So they thought, let's just have like the boosters go in a big orbit outside of the Earth-Moon system orbiting the sun. And it turns out one of the sensors was off by about 40 kilometers, I think, per hour. And so rather than doing a nice orbit, it did a strange orbit around the Earth, and then eventually so it was pulled by the sun and went around the sun, and then 30 years later, it came back to the Earth. It was a small error, but it was enough to make a difference. We want to figure out stuff like that. Okay, so just a couple of advice for my brother. Party less than the person next to you. If anybody's sitting by themselves, it's going to be a difficult semester. Take advantage of office hours and mentor. We have 2 TAs for this class who will be available consistently. First office hours for them will be Sunday at 8 o'clock. I am always up to meet with people. If I'm in my office, it's office hours. I have 2 kids, so I'm often doing shuttling detail. Unlike most professors, I am not going to try to get to know you. Your job is to make me get to know you. And it doesn't have to be me. You want to have at least one professor each semester get to know you well. That way, if you're only successful half the time, you not only have people who can write letters of recommendation for you, but you have people who will be aware of what are you interested in, what are your skill sets, what might be good opportunities that they could pass along. We don't have many postdocs here. We don't have graduate students here. Whatever opportunities we have, we give to the students. So I've worked on many multi-million-dollar lawsuits where students, often freshmen, are getting paid $60 an hour to do basic math stats. There's a lot of opportunities for projects like this. So always up for going for a walk, grabbing a coffee, grabbing a meal. Our last one is learn how to manage your time. This is extremely important. Homework in this class will be due, for the most part, every class. So there'll be a small number of problems to do. Math builds on itself. If something is coming up, by all means, just email me and say, hey, something's come up. Can I hand it in late? I will drop whatever homework assignment helps you the most. I do not do anything if you give me less than a day's notice, unless there's something truly exceptional. I've just been invited to the White House to receive, the National Medal. Sure, that's acceptable. But for the most part, you should be able to plan accordingly. If things are coming up, you adjust your schedule to make sure. There's not that much homework today. There was to read the Michael Uslan story. Start reading ahead in the books. Build up a strategic reserve. That way, as the semester happens, hopefully you'll be a little bit ahead in the lectures, and you can just keep going like that. I'm also happy to do practice interviews with people. This is more valuable the older you get, although as years and years pass, when people start applying for the big internships, is getting earlier and earlier in their career. And now a lot of sophomore internships are leading to the jobs people get after college. When you're a senior, it's often a fifth class getting ready for what you're going to do post-Williams. And you're always happy to meet with people. Please have your cell phones on silent or vibrate unless you're expecting a truly important call, and then just let me know in advance. So we have an option on cell phone policy. Option 1 is if someone's phone goes off, everybody gets a pop quiz the next day. Option 2 is whoever's phone goes off brings breakfast for everyone. What do we decide? Option 2, yeah. Okay, so you are welcome to try to call my cell phone during class, or have one of your friends try to call my cell phone during class to see if I forgot to turn it off. Okay. In terms of mechanics, there will be at least 2 midterms. I will drop whichever midterm helps you the most, unless you tell me otherwise. So unless you tell me otherwise, I will drop whichever midterm is your lowest score. I have been at schools where that is not always what a student wants to do. And you can try to imagine, why would you not want to drop your lowest score? So I'll leave that as a nice intellectual exercise if you can come up with a conceivable situation where somebody would actually prefer to have a lower score than a higher score. So there will be a final. Final is, I think, 45% midterm, 40% your average over all the midterms, and then homework is 15%. In terms of class participation, if you say something, that's great. So whenever you make a comment, please email me. This is for several reasons. One is it will help me to get to know all your names and who you are. 2, it'll help reinforce the material by just writing down, hey, Professor Miller, I'm the one who made the comment about easy functions to integrate, or the angles that were nice, or something like that. If you say something wrong, there will be no penalty for saying something wrong. But if you say something right, I will keep files so that if I have to write a letter of recommendation for you, I can do something that's non-trivial. The more detail I can give, the better. Sometimes what you think might be a really straightforward answer is actually very hard, and a lot of people miss it. But the most important reason to do this is it is hard to speak in public. I was an introvert until graduate school when one of my friends told me I should run for social chair. And initially I was a little bit skeptical because I said, don't you want somebody who enjoys being with people to be your social chair? I'm not really sure. And she said, would you compete? So that night at dinner, I asked my friends, if somebody else will run with me, there's 3 positions, I'll do it. And one of my friends said, sure, I'll do it. And it was one of the best things that I ever did in my life. It really got me out of my shell and got me to the point where I could start speaking with people. It's hard for a lot of us. The more you do it, the easier it is. This is why I try to ask a lot of questions in class, try to find something to speak up on. And again, it's just trying to get into good habits so that you will be noticed. There's a lot of people out there. How many have heard the phrase, you're one in a million? How many have heard the rest of the phrase? Which means there's 1,000 like you in China or India. So put things in perspective. You need to find ways to be noticed. Okay. Any questions on the mechanics up to now? Okay. So we will eventually get to calculus today. But what I want to do is I want to start talking a little bit at a higher level. You know, I mentioned I'm not allowed to lie. I am allowed to mislead. I will be brutally honest. Most of you probably will not be using the specific math you're learning in this class ever. You'll have computers that will be doing this for you. What's more important is learning how to set up problems, learning what types of problems are solvable, learning how to present information. Can anybody tell me what this is a map of? Yes.
All Americans rooting for the Super Bowl.
Okay, which Super Bowl? Do you think this is the Super Bowl from this year? It's not this year. Anybody know which teams were playing? I'll zoom in a little bit. Patriots are one of the teams, and the other team, the Rams. So this was from a couple of years ago. What do you notice about the country? Yes. Everyone? Most. Okay, so what can we learn from this picture? Who's willing to root for the Patriots? New England. Okay, does that make sense that New England is rooting for the New England Patriots? Yes. Anybody else rooting for the Patriots? I'm sorry? Louisiana. I'm actually going to Louisiana later today to meet with one of my colleagues who is part of a Pulitzer-winning team for the papers down there. And he shared some stories with me as to why they were rooting for the Patriots in the Super Bowl and what they did during the Super Bowl. So do you know why?
I'm an international student, I don't know.
Okay, just so you know, as I was running. So why would Louisiana, and maybe I'm phrasing it wrong, maybe they're not rooting for the Patriots. Anybody? Football scholars? Yes. So you're halfway there. There was a horrible uncalled pass interference, which if it was called, the New Orleans Saints would have had a first down, chip shot for the field goal to win the game, and they could have run out the clock. After the game, it was so bad, the NFL apologized and said, yeah, wow, we really missed that one, huh? Sucks to be you. And so they were so furious in New Orleans that a lot of the bars did not broadcast the Super Bowl. They actually played an old Super Bowl that the Saints were in from years earlier. They were just so furious. But the reason I'm saying this is you want to be able to look at data, look at images, look at maps. What can you extract from it? Whenever you see something going on that's non-standard, there might be something interesting happening. Anything else we should notice on this map? Part of it might depend on how good your eyes are. Yes. Yeah, there's a little section of Patriot fans. You know, is it maybe people from New England who are driving to the Super Bowl and they just happen to be over there when everybody's pressing their buttons as to whom they're rooting for? Anybody know where that is? It's St. Louis. So any football fans who might figure out why St. Louis was rooting for the Patriots? The Rams left St. Louis. So it's not necessarily when they say, just because they say it's who America is rooting for in the Super Bowl, it might be, I'm not rooting for the Patriots, I'm rooting against the Rams. But when you look at this plot, there were three places that were very different, and there's a story behind it. You want to figure out, how do you present information in such a way that it can be meaningful and impactful? Most of you are not going to be owning a Fortune 500 company as soon as you leave Williams. You will have bosses over you, and you might have to convince them to do what you want, that you have the right analysis. How do you convey? When you want to present mathematics, how do you present mathematics in such a way that the argument is clear? One of the best statistics I ever heard was talking about how energetic radiation is. Is there anybody who has enough of a physics or chemistry background that if I gave you radiation values, this would be meaningful to you? Okay, who here has ever gone to the dentist and had an x-ray? What does the dentist or the hygienist do? Yeah, they put on a lead apron and then they leave the room. Or they go far, far away. Why do they put on a lead apron? To block the radiation. And again, they're not doing it to you so often that it's that bad, but let's protect you a little bit. So I was reading a book that was trying to describe how energetic some cosmic radiation was. And they said, imagine a lead apron stretching from the sun to Pluto. It would pass through that without any trouble. Okay, I now have a sense of how strong this radiation is. It was a great way to present. So when you're thinking about how to use math in what you're doing, you always want to think about how can I present this in such a way that will be meaningful. Right. So I did a little web searching today and I found a really nice plot of sunrise and sunset times on the East Coast. And I was able to get Providence, Rhode Island, Orlando, Florida, and Washington, DC. I'm not quite sure why they're ordered in that way. It's not alphabetical. It's not by, anyways. What do people notice about sunrise, sunset times? They change with the seasons. Do they change continuously or discretely? Yes, both. So is it mostly continuous, mostly discrete, or more like half and half? Mostly continuous. Can anybody think of why it's occasionally discrete? Yes. Daylight savings. And in fact, you can tell quite clearly, the two times when daylight savings is happening. So when you look at this, there's something interesting happening. Either something is happening to the Earth's orbit, or something is happening to how we're measuring time. So again, when you see information, you always want to ask what's going on. You want to try to understand the plot as much as possible. All right. So what I want to do now is, talk a little bit more about the mechanics. What are we going to do in this class? Why do we care so much? So I'm going to talk about integration, which you've hopefully seen. How many of you have seen a proof of the fundamental theorem of calculus? All right, so a lot of people, it's Moses comes down from Mount Sinai, and if thou integrates this, thou shalt get the area. And it shall be the antiderivative. Okay, so we will give a proof of the fundamental theorem of calculus for one variable. We will not do a proof of the analog in several variables. If you really care about that, you can either talk to me, try to generalize the argument, take more math classes. I want to do enough so that you have a sense of what's going on. The big thing is dealing with a limit, is passing from these Riemann sums, these sums of rectangles, to the areas under curves. But I want to just choose a specific example and try to warn you about how careful you have to be and how easy it is to get the wrong lesson from what's going on. I am a huge fan of Mark Twain. One of my favorite quotes of his is something like, "A cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. To each experience in life, only draw from it what you should." I will send an email later if I remember about another version of a stove quote, which I think is very fun. But you want to be very careful. Just because something looks like it's working for a while doesn't mean it's always going to work. For example, let's see how well people are with division. 16 over 64. 1/4. It's a little slow. It's 9 a.m. 19 over 95. 1/5, getting a little bit better. 49 over 98. 1/2, good. 12 over 24. I'm sorry. I get 1/4. Am I making a mistake? Yeah. Do you want me to show my work? All right, 16 over 64, we cancel the 6s and we get 1/4. 19 over 95, we cancel the 9s and get 1/5. 49 over 98, we cancel the 9s and get 4/8, which reduces to 1/2. So clearly, Now, the other way to do this is I actually don't give you 49 over 98. I keep that in strategic reserve. And if you doubt me, say, well, let me try another fraction. Let me try 49 over 98. Just because something works a couple times does not mean it's always going to keep working. That's why we have classes like real analysis to put subjects like this on a firm foundation. And when calculus first came around, there were some real concerns about the underlying rigor. And the notion of rigor has definitely changed over time. Right. So I am a huge fan of physics, science fiction, astrophysics. In previous years, I've actually done trips to the rear books section at the library here, and we can actually see a first edition Copernicus, Galileo, Kepler, Principia from Newton. And so if people are interested, we can definitely try to do a field trip later. Is there anybody here who has not seen Newton's law of gravity? That the force between two masses is proportional to the product and inversely proportional to the square of the distance. So one of the big inspirations for Newton's development of calculus was he wanted to try to figure out what is the force exerted from one body on another. Well, the simplest example is imagine you have two spheres. Without loss of generality, that's a huge phrase in mathematics, we can always assume that we orient our system so that the second body is over the north pole of the first. Who here has ever played tic-tac-toe? If someone can beat me, I will give you $1,000. But if you don't beat me, you owe me 10 cents. Does anybody want to play? You got 10 cents on you? Oh, I've been around long enough not to play without the cash on the table. What do you think the odds are that I'm going? Now, again, I could slip and go in the wrong square. And say, 10 cents, it's worth it. I'll take the risk for 10 cents. Tic-tac-toe is a very easy game to analyze. How many opening squares are there for my first move in tic-tac-toe? 9. By symmetry, how many opening squares are there? 3. There's the 4 corners, and I can just rotate the board. They're all the same. There's the 4 middles. They're all the same. And then there's the center. If you look at those 3 configurations, you can then ask for each one, how many second moves are there? From the corner, it turns out there's 5 distinct types of moves. From the middle, 5 distinct. And from the center we can do in our head. If I move in the center, how many distinct responses are there? 2, corner or middle. There's only 12 pairs of opening moves. That's much better than 9 times 8. This is a big thing we try to do in math as much as possible. Reduce whatever you're studying to something simpler. What are the key features that matter? How many of you have heard of Galileo's experiment where he dropped 2 spheres from the Tower of Pisa? To try to show that the mass doesn't matter, that they'll fall at the same time. Very famous experiment in physics. So for those of you who heard it, what were the color of the spheres? So why don't you know? Is it because our educational system sucks?
Because that's irrelevant.
That's irrelevant. Now, I can give you a situation where the color actually does matter. Different colors might absorb heat differently. Maybe I take one that's black and one that's white, and I put it out in the hot sun for 8 hours. Now they're at different temperatures. And now when I drop them, maybe the temperature of the object could affect how long it falls through the air. Maybe not, but at least there's a possibility now. But if you have 2 objects where the only difference between them is color, no, that should not matter. It doesn't really matter what color they were. It's try to find which things really matter. So when we're trying to analyze what's the most basic model we can study that captures all the key systems. So here's one possibility. Well, I've got a lot of computing power. What I'm going to do is, rather than having a continuous sphere, let me take some kind of lattice points. So I'll put points, and I'll just only look at the points that are inside the sphere. And I'll divide the mass of the sphere equally among each point. And as I take more and more points, that should converge to what the sphere does. And in the limit, as the distance between the points gets smaller and smaller and smaller, it's going to get closer and closer and closer to the continuous case. And I hope that this would be a great approximation. So that if maybe I could calculate the force in this finite case and take a limit, I could then prove that in the end, I will have the same force as if all the mass were concentrated at the center. I can do that calculation very simply, just put all the mass at the center and calculate. And I'll compare to what I got here. And I'll look and see how close are they relative to, the gap between them, the spacings. The more points I have, I would expect the closer approximation it should be. So when I'm trying to compare these, we talked about pictures before. What picture would you like me to show you? What should the x-axis be? What should the y-axis be? So I have all the mass at the center, and I have a lattice with some separation, just looking at how many points are inside the sphere. Say a sphere of radius 1. So what should the x-axis be? What am I going to be varying? The distance between the 2 points or the number of points I have. Excellent. So that's my x-axis. What should the y-axis be? So the x-axis is going to be the distance. What should the y-axis be? What's the height, though? What quantity would I want to look at? Yeah, the force. Look at the force from each one of them. And so, here is some simple code. It's extremely valuable to learn how to program. And so this is a really simple program I wrote in Mathematica to just do the calculation. And we will do, some learning how to code here. I used to say that if you could code, if you knew probability and you knew statistics, you could always get a job. I can't say that because someone actually sued their college when they didn't get a job after graduating. They actually discovered a new type of discrimination previously unknown to students. Academic discrimination. They claimed their school did more for students with higher GPAs than lower GPAs. And that wasn't fair, that their 2.6 was just as good as someone else's 3.6. They also misspelled tuition in their lawsuit. It's amazing what you can find with the Freedom of Information Act. But I can't guarantee you a job. If you have these basic skills, it's incredible how many openings there will be for you. So just learning how to do very simple coding is wonderful. It's valuable. This allowed me to do a little bit of comparison. And now I plot it. So the left is showing a plot of the discrete case versus all the mass at the center. The right is looking at the difference. And the reason I'm looking at the difference between the forces in the two cases is their values are so close, it's hard to tell what's going on. Somebody give me the name of a rich person, but not a super, super rich person, not an Elon Musk level. Okay. Ooh, he's a billionaire though, isn't he? Yeah. President of the college. Great, this is being recorded. Wonderful. All right. I'm sorry? Okay. All right, so we'll take the president of the college. Very nice salary. Probably has saved a bit of money over the years. Probably a millionaire by now. If we look at a plot of Elon Musk's wealth and Elon Musk's wealth plus President Mandel's wealth, would you notice a difference? No, completely noise. Let's throw in all of us as well, okay? We'll throw in this section, and I'll even put myself in, okay? Would we notice it at all? No, but if we looked at the difference, we would actually then see something significant. Oh, there really is a sizable difference. And so when you have things that are extremely close and differ to low orders, if you just plot their values, you're not going to see anything meaningful other than they look pretty much the same. You're going to miss the lower order terms. So when we subtract, we see the lower order terms. What do you think is happening as the division gets finer and finer? What do you think happens to computing the force by putting all the mass at the center versus computing the force by this discrete approximation? So look at the plot. What do you think is happening? I'm sorry? So this is the difference between the two forces. So if I compute this quantity two different ways, if I compute it with all the mass at the center versus computing with a discrete approximation, and it looks like they're the same, there's a little bit of a difference. But what's happening to the difference between them as the distance gets smaller and smaller, as I take more and more points, as I take a better and better approximation? What seems to be happening?
Closer to infinity, I would consider a moment.
What do you mean by getting closer to infinity?
Here it's going to negative 11.
Well, but this is 10 to the -6, -8 times 10 to the -6 times 10 to the -4 times 10 to the -6, -2 times 10 to the negative. What's happening to those values, those blue dots, as I take more and more points? Yes. It looks like it's approaching 0, right? As I go further and further down, doesn't it look like it's getting closer and closer to 0? Do you think this is a proof that it goes to 0? No, I mean, the problem is it's really hard to tell. What if the difference is of size 10 to the -8? That would be about 1%, 10 to the -10. I can't really see anything that fine. Over here, do you see any difference between the dots? If so, I mean, my eyes are terrible. I can't see things that are close to me. If I go to the back of the classroom, I might have a chance. They look the same. When we look at the difference, we start to see, okay, there is a bit of a difference. It looks like it's going to 0, but this is not a proof. Remember, we had that 16/64. Just because something works for a while doesn't mean the pattern is going to continue. But it's suggestive. And if you had to make a conjecture, if you had to guess, what do you think would happen as the mesh gets finer and finer, as the distance gets smaller and smaller? What's the natural conjecture? It's going to 0. And it turns out that that is the case. This was a huge motivation for Newton to develop calculus, to be able to prove something like this so that you could actually start doing these calculations for planetary motion. I'm going to assume nobody here has taken a class in special relativity. I still remember one of the lines from my physics textbook in high school, and they had a very low-level introduction to special relativity, and they said something along the lines of, these results may seem a little surprising at first, but you have to remember most people don't have experience traveling at 3/4 the speed of light. I liked the most. Even the Flash, Superman, Supergirl, they're not hitting 3/4 the speed of light. So one of the biggest problems in life is taking something that works in one regime and extrapolating to another. So imagine Einstein is the god of the subject. Back then, the fast way to travel was by a train. So examples are usually on trains. So imagine you're on a train traveling at 100 miles an hour, and you're jogging at 10 miles an hour in the same direction as the train. Somebody on the ground, how fast do they see you moving? So train's going 100 miles an hour, you're going in the same direction on the train, jogging at 10 miles an hour relative to the train. How fast does somebody on the ground see you traveling? I'm sorry?
90 miles?
Well, you're going in the same direction as the train. 110. Does everyone agree it's 110? Well, what you'd have to do is you'd have to measure that. And the question is, how accurately can you measure it? And unfortunately, we can't measure it, or at least in 1900, we couldn't measure it to a tremendous degree of accuracy, 4 or 5 digits maybe. But what if the difference is much, much smaller? And it turns out that if you have 2 different speeds and you want to add them, the speed that somebody sees on the ground is not just the sum of the speeds. There's a small correction factor. You divide by 1 plus the product of the speeds divided by the square of the speed of light. Does anybody know approximately what the speed of light is? In either the metric system or the English system. 186,000 miles a second. Anybody know roughly how fast, say how far California is? Roughly, how far is California? Or what's the equator diameter of the Earth, approximately? God, this is your ballpark, guys. It's about 24,000 miles to go around the Earth. If you go 186,000 miles in a second, how many times would you go around the Earth in 1 second? Approximately. Around 7, right? So in 1 second, light would go around the Earth about 7 times. Okay, that's light. If we're traveling at 100 miles an hour, and it's, oh dear God, it's much longer for us to go all the way around the Earth. This correction factor is so small, we can't even notice it. And so just because it looked like speed was additive, that's not a proof. It's just in the range we're looking at, we can't see a difference between speed being additive and not. The correction would be so much smaller. And so again, you're trying to find ways to display the information. So I have a train or rocket ship traveling at 10,000 miles per hour, and we shoot a projectile in the same direction as the train or rocket ship. And I want to see what is the correction factor. And so if the projectile is not moving, what a surprise, there's no correction factor. Always look at extreme cases. Is this reasonable? Yeah, it's kind of reasonable if the projectile is not moving, that there would be no correction factor. And then as you get all the way up to 10,000, which is the speed of the rocket ship, the correction factor is 4 times 10 to the negative 6. So we're basically talking about 10 to the negative 6. 10 to the 6 is a million. So maybe 4 out of a, that's really small. 4 parts out of a million. That's going to be very hard to notice. And so even in a situation like that, it would be very hard for us to see that. Now with cell phones and GPS systems and whatnot, we can actually see effects like that. And they do have to take into account special and general relativity to have everything working as well as it does. But when we're trying to do observations from the early 1900s, that's way beyond the level of precision. Over here, the speed is getting a little bit faster. And now you can see we're beginning to get 2,000 miles an hour up to 8,000 miles an hour difference. It's still small relative to the speed, and it's going to get incredibly high as we get closer and closer and closer to light speed. But this is the danger of trying to extrapolate from one regime to another. Any possible physics majors here? Okay, so this class is going to emphasize the Taylor series, but we will talk a little bit about Gauss-Green-Stokes theorem, because that is stuff you need to know for physics, where we'll make sure we cover that. The great Richard Feynman had a wonderful quote about just how accurate quantum mechanics is. And he said, it's basically, the results are so accurate, it's on the order of measuring the distance from Boston to Los Angeles to within the thickness of a human hair. I don't know if he's talking about the width or the height. It doesn't really matter. I mean, one is more impressive than the other, but just, even the longest hair we have of anyone in this class, if you can get the distance between Boston and LA that precise over that many orders of magnitude, that's amazing. One of the things we will do later in the semester is talk about logarithms. How many of you have done logarithms in high school or college? How many of you know why we do logarithms? There's a lot of material like that in high school where it's in the curriculum, so we do it. Does anybody know why we give a shit? Oh, sorry, this is being fun. Does anybody know why we care about logarithms? Why do we care about logarithms? Great, they help us with comparisons. If you want to compare things across many orders of magnitude and have things on the same scale, if we compare ourselves directly with Bill Gates, Bezos, Musk, too many orders of magnitude. If you compare the size of a proton to the size of a galaxy, too many orders of magnitude. But by taking logarithms, now all of a sudden something that differs by 10 orders of magnitude, if you're doing logarithms base 10, it's not much of a difference anymore. So that's one reason we do logarithms. The other is logarithms can often linearize nonlinear relationships. A straight line is the most basic important object that we have. It's the easiest thing to understand. And so if we can reduce something to a straight line, we have a much better sense of being able to understand it. So this is a little bit of a motivation of what we're going to be doing. We're going to be learning multivariable calculus. This is calculus of several variables. A lot of it is, well, if you did something in one variable, do it again. And now we just have more variables to play with, which means we can have a better model of what's going on. So when you do things in calculus of one variable, you have, okay, I have my input variable x, and then I have my output variable y, and y depends only on x. Most things in life don't depend on just one item, and you have the ability to change many things. Do we have any econ potential majors here? Okay, so if you're trying to figure out, what should U.S. policy be, you have lots of things you can play with. You can play with the interest rates. You can play with the tax rates. You have so many different things you can play with. And what's the right strategy? And depending on where you are, different choices will lead to better solutions. All right. Any questions on the mechanics or just the basics of the course? Okay, so we have 5 minutes left. And so with 5 minutes left, I want to just start off with just 1 or 2 key ideas from Calc 1. And then I'm going to give you over the weekend a set of homework problems with solutions for calculus. And I just want you to look at them. You're welcome to try to do them without looking at the solutions. You're welcome to look at them with the solutions. And then just let me know, are there any particular parts you want to review? And so I want to spend the first class, maybe 2 classes, just reviewing Calc 1, Calc 2 quickly as a way to build and transition into Calc 3. There's plenty of time to do this. It's worth seeing things, and we will then define things a little bit better. So when we go back to Calc 1, we're not going to define things exactly as you've done it before, because that definition doesn't quite generalize as well. And so we're going to try to talk about how should we define things so that when we get to several variables, it's going to work well. All right, so the big idea from Calc 1 is the notion of the derivative. So can somebody give me the definition of the derivative? Yes. So it's the tangent line. And so what I can do is I can draw my function, and maybe here's my point x, and then here's my point x plus h. And what I can do is I can calculate what's called the change in f or the change in y over the change in x. And so the average rate of change from x to x plus h is going to be f of x plus h minus f of x over x plus h minus x. What's the more common way of writing x plus h minus x? H. And so what we do is the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. And in the limit, that's going to give us what's called the tangent line. And so we have to talk about how do we actually calculate this limit? Does this limit always exist? The other thing that's worth commenting on is how we name the derivative. So we sometimes also write df dx. Does anybody know why we often write f prime? So you always want to think about, why do you give something a name? Who remembers their trig? I mean, really remembers their trig. Who knows what trig is? Okay. What's 1 over cosine? What's the name of that function? Nope. 1 over cosine is, it's secant. What's 1 over sine? Cosecant. Wouldn't you want cosine and cosecant to be together and sine and secant to be good? There is a reason why there's things called coangles. It makes sense when you understand. But when you're first looking at it, you go, someone really hates me. This is bad notation. F prime. Oh, okay, it's something related to F. F is part of its name, and there's a prime. Okay, it's related to F. What do we use to represent the antiderivative? Integral. But what letter would we use, or notation would we use for the integral of little f? Capital F. And again, You don't have to use it, but by doing that, it makes it a little bit easier when you can quickly glance down and see what's going on. So you always want to think about notation. You want to think about names. This is the definition of the derivative. We're going to revisit this next class in a way that will generalize to multivariable, and we'll then just quickly review what you should have done in Calc 1 and Calc 2. I am not going to hold you responsible for painful integration techniques. The integrals I give you will be nice. If you want painful integrals, please ask me. I will happily give them to you on the side. This is not a class in painful integral techniques. This is a class in using calculus to do problems. If you have any questions, I am happy to chat, but this is a good time to stop.